Hello students, welcome to AII. I hope you are doing good at your study. So from today onwards we are going to start a very special lecture session, and that is the easy notes of the CRE2. In this particular lecture session we will cover the very prominent topics of the CRE2 that is very important from exam point of view, because we find they used to appear as a question in our exam. So from the first lecture, or in this particular first lecture, we are going to take the first topic of the CRE2, that is the kinetics of heterogeneous reaction. And in the kinetic of heterogeneous reaction, what is very important, that is how to write the rate law for the heterogeneous reaction and what is the effective rate constant. We will first understand the theories of these two things, and then we will consolidate this theory by solving two numerical problems. So let us start. Now, here you have to note down two important things, that while dealing with the heterogeneous reaction, that you have to consider two steps. One step is the mass transfer step, and that is associated with the mass transfer from the bulk phase of the component, or you may say the reacting component, towards the solid surface. And second is the chemical reaction step, and that is nothing but similar to the reactions which you have studied in the kinetic of homogeneous reaction. Why I am considering these two steps? Because these two steps will help us out to write the rate laws. So while writing the rate law for the heterogeneous reaction, what you have to consider two steps, that is the mass transfer step and the chemical reaction step. Now, if the heterogeneous reaction is taking place in the competitive manner or the simultaneous manner, so in that case the rate law or your overall rate will be nothing but the summation of the individual rate. Okay, so here that you have to mug up this thing, that in case of the competitive reaction, or if the heterogeneous reaction is taking place in the parallel manner, so the overall rate R overall will equals to the summation of the individual rate. Okay, now if the heterogeneous reaction is taking place in the successive manner or in the series manner, in that case the overall rate will be nothing but the individual rate. So you have to mug up these 2 points. In case of the parallel reaction, your overall rate is nothing but the summation of the individual rate, and in case of the series reaction, your overall rate is nothing but the individual rate. So what you are doing, that in case of the competitive reaction, you are adding the rate laws, while in case of the series reaction or successive reaction, what you are doing, you are comparing the rate laws. Okay, now we will understand how to develop the rate equation for the heterogeneous reaction. Okay, now for that I am going to consider a heterogeneous reaction. You must be aware about the heterogeneous reaction, that is nothing but a chemical reaction which involves more than two phases. Okay, so here I am considering a gas solid heterogeneous reaction, and here I have a component in the gas phase, and it is going to deposit over the solid surface B, and it is forming a product R. Okay, so it is a kind of a heterogeneous reaction. So while considering a heterogeneous reaction, after considering the heterogeneous reaction, what we will do, we will write the rate law, or we will try to write the rate law for this heterogeneous reaction. So what we have to consider, we have to follow these two steps, that is the mass transfer step that is taking place as a result of the diffusion process. Okay, so here the rate law will be given as minus RA double dash. Okay, minus RA double dash, because I am going to write the rate law on the basis of the unit surface area of the solid catalyst. So minus RA double dash, or unit surface of the area of the solid catalyst, or unit surface area of the interface. So minus RA double dash, that is equals to what? Minus 1 by S dNA by dt. Okay, this you have mug up in your CRE1, that is the kinetic of homogeneous reaction, where we come to know about the various method in which we can write the rate law expression. So minus RA double dash equals to minus 1 by S dNA by dt, and if you are writing the rate law for the mass transfer step, that will be equals to minus RA double dash is equals to kg into concentration of A in gas phase minus concentration of A at solid. Okay, Ca is the concentration of A in the gas phase or the bulk phase, and Cs is the concentration of A over the solid surface. Okay, where kg is the mass transfer coefficient. Okay, now listen, let us assume this is the first rate law. Okay, now what we will do, after the molecular diffusion of the component A from the bulk to the solid surface. What happened? Now the solid surface has been absorbed over the catalyst. Now the reaction or chemical reaction will take place. So when the chemical reaction take place, we have to write the rate law. So the rate law expression will be the very similar that we have studied in the kinetic of homogeneous reaction, and that will be minus RA. Let's say this is RA2 double dash, and here that will equals to K double dash into concentration of A at solid surface. Here I am assuming the first order kinetic. For simplicity, I am considering the first order kinetic. Okay, so this is the rate expression for the mass transfer step, and second one is the rate expression for the chemical reaction step, assuming the first order kinetics. Okay, let's say this is your equation number 1, and let's say this is your equation number 2. Okay, now what you are finding that after this particular step, this second step is taking place. That means the reaction is successive in nature. So here the overall rate will be what? Overall rate will be nothing but the individual rate. So what we will do, we will write the overall rate now. So the overall rate will be now overall rate, R overall, that will be nothing but minus of RA1 double dash minus of RA2 double dash equal. Please put the equal sign. Okay, now what we will do, we will compare the rate. Okay, we will compare the rate. So here we will have kg into concentration of A in gas phase minus concentration of A at solid phase mine is equals to K double dash. K double dash is nothing but the rate constant. K double dash into concentration of A at solid surface. Now, what we assume that this is the condition at steady state. This is the condition at steady state. Okay, this is the condition at steady state. So at steady state, you can compare the two rates. Okay, so when you are comparing the two rates, what you will do, what you will try to figure out from this particular comparison, you will try to figure out the value of the CAs. Why is the value of the CAs? That is the concentration of A at the solid surface, because we assume that the concentration of A at the solid surface is comparatively lower than that the concentration of A in the bulk phase. Okay, so we will find out the value of the CAS. So CAS, if you try to figure it out, you will find that is kg into CAG to that of kg plus K double dash. Okay, this is the value of the concentration of A at the solid surface. Now let's say this is your equation number 3, and put this equation number 3 in any equation. Let's say in equation 1 or equation 2, you will have the value of the overall rate. So the overall rate finally you will have, if you put, let's say you are going to put it in equation second. Let's say you are going to put it into equation second. You can put also in equation 1, you can get the same result. So if you put it in equation second, so R overall, that will be equals to kg into K double dash to that of kg plus K double dash into CAG. Okay, you have to mug up this relationship. So this is the rate expression for a heterogeneous reaction. Okay, assuming first order kinetics. Now this particular term is called the effective rate constant. This particular term is called effective rate constant. So it is represented like this, K effective, and that will is equals to kg into K double dash to that of kg plus K double dash, or you may find, or 1 by K effective is equals to 1 by kg plus 1 by K double dash. So you have to mug up this relationship, because in your gate examination this particular relationship has been asked 3 times. Okay, so furthermore they are not going to ask this particular relationship, or if your luck good, if your luck is good enough, is very good, then you may get this particular relationship one more time in your examination. Otherwise what they will do, they will provide you the numerical value of this kg and K double dash, and you have to evaluate the value of the K effective, or they may ask you the value of the or magnitude of the overall rate after providing you the value of the kg, K double dash and CAG. So this is about the rate expression for the heterogeneous reaction, and this particular relationship, that is the effective rate constant, that you have to mug up. Okay, now we are going to solve 2 numerical problems so that we can consolidate about this theory. Okay, so let's start. Okay, now please go through this particular question. What is saying given in this question? A gaseous reactant diffuses through a gas film and reacts on the surface of non-porous spherical catalyst particle. The rate of surface reaction is K1CS, where CS is the reactant concentration on the catalyst surface. The reaction rate constant K1 equals to 0.83 into 10 to the power minus 4 meter per second, and the gas film mass transfer coefficient Km equals to 1.66 into 10 to the power minus 4 meter per second. Find the reaction rate expression in terms of bulk gas phase concentration of C0. So what you have to do in this particular question, you have to find the value of the rate law. You have to find the value of the rate law in terms of C0. Now, what you are finding that in this particular question, you are finding that the gas is going to diffuse over a solid surface, that is nothing but a catalyst, and here we have the rate of surface reaction is K1CS, that is nothing but the chemical reaction step, where CS is the reactant concentration on the surface of the catalyst. They have provided some data about the K1 and Km. Now what is K1? That the reaction rate constant, which we have denoted or which we have studied, that will be nothing but K double dash. Here K double dash or K1 is nothing but K double dash. Okay, now what about Km? Km is the gas film mass transfer coefficient, so we know that this will be your Kg. Okay, C0 is the concentration in the bulk phase. So how we have studied about this thing, that is CAG. Okay, what you have to find the reaction rate expression. So the reaction rate expression will be the similar which we have already gone through. So we will have a rate is equals to K, or if I write in this fashion, K1 Km. Okay, or if you want to write in the earlier one manner, you can write that is K double dash into Kg over K double dash plus Kg into CAG. Okay, and if you use this notation that is given to us in the question, that will be K1 into Km to that of K1 plus Km into C0. You have to simply put the value of the K1 Km and get the result. So if you put the value of the K1 Km, so the value are 0.83 into 10 to the power minus 4. This is for K1. Then we have Km, that is 1.66 into 10 to the power minus 4. Then divided by 0.83 into 10 to the power minus 4 plus 1.66 into 10 to the power minus 4 into C0. Okay, after solving you will have the final result, and that is rate is equals to 0.55 C0. This is your answer. If they will provide you the value of the C0, that is the bulk concentration of A, you have to put it here and get the magnitude of the rate. Okay, so this is the question that has been asked in the GATE examination in the year, I believe so, 1995-96. Okay, so similar kind of question that they may framed you in your upcoming GATE 2024. Okay, now we are going to take one more problem. Okay, so that we will understand this concept in more better way. Okay, let's take another numerical problem. Now please go through this particular question. Gaseous reactant A diffuses through a gas film in the surface of the solid B, where it reacts with B according to the reversible first order rate minus Ra double dash equals to K double dash Cas minus Cae mole per meter square second, where Ca is the concentration in the equilibrium with the solid surface. What is the rate law that accounts for both the mass transfer and the reaction step? So what you have to do, you have to develop a rate equation, and that consider both effect, mass transfer effect as well as the reaction effect. Okay, now already they have given you a rate law, and this rate law is regarding what? This rate law is regarding the chemical reaction step. How I come to know about this thing? Because here they are saying that the gas A is diffusing, okay, over the solid surface B. So when the gas will diffuse over the solid surface B, what it will do, that it will simply undergo the chemical simply a chemical reaction will take place after absorption over the surface of the solid. what you will find, the chemical reaction will take place. So this rate law is nothing but the rate law associated with the chemical reaction step. This rate law is associated with the chemical reaction step. This rate law is associated with the chemical reaction step. Now we have to develop the rate law for this particular condition. So how we will develop this thing? We will follow the same approach. First of all, gas A will diffuse through its bulk phase to the interface or to the solid surface. So the diffusion process is involving, so we have to write the rate law on the basis of the mass transfer effect. So the mass transfer step, rate law as per the mass transfer step, that will be minus RA, let's say double dash, because we are writing on the basis of the unit surface area, because this notation is for the unit surface area. RA double dash 1 is equals to, that is nothing but kg into concentration of A in bulk minus concentration of A at solid phase. Let's say this is your equation number 1. Now second step will be the reaction step or chemical reaction step. Okay, now the chemical reaction step, they have already provided us that minus RA2 double dash equals to K double dash concentration of A at solid phase minus concentration of A at equilibrium. Okay, these are the two equations. Now these two steps are taking place in the successive manner. That means the overall rate will be nothing but the individual rate. So what we will do, in order to get the overall rate, we will simply compare these two rates. So when I will compare these two rates, let's say if I compare equation 1 and equation 2, so what I will have, that is kg, I will have kg concentration of A in gas phase minus concentration of A at solid is equals to K double dash concentration of A at solid phase minus concentration of A at equilibrium. Now what I have told you, that the concentration at the solid surface will be less compared to that of the concentration of A and the bulk phase. So what we will do, we will try to find out the value of the CAS. So the value of the CAS, if you figure it out, you will find kg into CAG plus K double dash into CAE to that of kg plus K double dash. This is the relationship for the CAG. You have to simply rearrange the equation. Okay, after rearranging, you will get CAS equals to kg into CAG plus K double dash CAE upon kg plus K double dash. Now let's say this is your equation number 3rd. Simply put this equation in any one equation, either in the mass transfer step or in the chemical reaction step. So what you will find, you will find the overall rate. So the overall rate, that will be equals to, let's suppose I am going to put it into the equation number 2nd. So that will be kg into, that will be K double dash into, in place of CAS I can put kg into CAG plus K double dash into CAE to that of kg plus K double dash minus of CAE. Okay, now if I solve this particular, I will have the overall rate, and the overall rate for this particular case will be K double dash into kg over K double dash plus kg into CAG minus CAE. Okay, so this is the rate expression for this particular case, where what we are finding, that the rate is the function of not only the concentration of A in the bulk phase, but also the concentration of A at equilibrium. Okay, but the effective rate constant is same that we have got derived for the case where there is no equilibrium condition case. Okay, so for this particular, the overall effective rate, K effective is the same, and that is K double dash Kg over K double dash plus Kg. Okay, so I believe that you have now understand the concept how to write the rate law for the heterogeneous reaction. Okay, simply you have to follow the mass transfer step followed by the chemical reaction step, and then you have to do the comparison of the rates, so you will have the overall rate. In order to get the overall rate, what you have to ruled out, you have to rule out that concentration which is limited one, and it is the concentration of the reacting species over the surface of the solid catalyst. So we used to find out the value of the concentration of A, let's say A is your reacting species, over the solid surface. Okay, and after having the value of the CAS, we can put this particular in any one equation, either in the mass transfer step or in the chemical reaction step, and we can have the rate law. Okay, once you will have the rate law, you can compare it by the simple rate law expression and get the value of the effective rate constant. So effective rate constant, that is very important from exam point of view. Please mug up this, that K effective is equals to Kg into K double dash upon Kg plus K double dash. Okay, I have made you solve 2 numerical problems regarding this. Now I believe that you have understood this concept. That is something very important in this particular chapter, that is the kinetic of heterogeneous reaction. We will discuss the other aspects of the CRE2 in our upcoming lecture. Keep in touch with me. Okay, that's all for today. Thank you so much.